In this video, I will talk about how to deal with unrestricted-in-sign variables in the Simplex method and their application in the production smoothing scheduling problem. In the previous videos, we talked about how to solve a linear programming problem when it is converted into the standard form. In the standard form, we want xj to be greater than or equal to 0. If we have a variable x that is less than or equal to 0, we can define a variable y which is equal to negative x, and y should be greater than or equal to 0. However, if we have a variable x that is unrestricted in sign, which means it can take positive numbers, negative numbers, or 0, then the problem is not in the standard form. To deal with this situation, for each unrestricted in sign variable xi, we need to define two new non-negative variables xi plus and xi minus. Xi plus denotes the positive deviation from 0, and xi minus denotes the negative deviation from 0. Then replace each xi with xi plus minus xi minus and add the sign restrictions. After that, we can apply the simplex method to solve the modified problem formulation. During the simplex iterations, the unrestricted-in-sign variable xi in every basic feasible solution must fall into one of the following three cases. Either the positive deviation is greater than 0, or the negative deviation is greater than 0, or they're both equal to 0. We will not have the situation that the positive deviation and the negative deviation are both greater than 0. Now let me show you an example. This is a maximization problem. We have two variables. x1 is greater than or equal to 0, and x2 is unrestricted in sign. For this problem, the feasible region is marked by the shaded area. We can solve it graphically, and point D33 is the optimal solution. Z star is equal to 15. Let's try to solve it using the simplex method. We need to introduce two select variables, s1 and s2, and make these two equality constraints. Then for unrestricted-in-sign variable x2, we introduce two variables, x2 plus and x2 minus. Replace each x2 with x2 plus minus x2 minus, and add the sign restrictions. This is the simplex tableau. In this tableau, s1 and s2 are basic variables, and others are non-basic variables. Let's set non-basic variables to 0 and solve for basic variables. s1 is equal to 9, s2 is equal to 9, and z is equal to 0. The entering variable will be x1 because it has the most negative coefficient in row 0. The ratio is the right-hand side divided by the coefficient of x1, 9 over 2 and 9 over 1. Row 1 has the smallest ratio, so it is a pivot row. We need to change this to 1 and make it disappear from other rows using EROs. This is the updated tableau. x1 and s2 are basic variables, and others are non-basic variables. Let's set non-basic variables to 0 and solve for basic variables. x1 is equal to 9 over 2, s2 is equal to 9 over 2, and z is equal to 27 over 2. The entering variable will be x2 plus, because it has the most negative coefficient in row 0. The ratios are 9 and 3, so row 2 is a pivot row because it has the smallest ratio. We need to change this to 1 and make it disappear from other rows using EROs. This is the updated tableau. x1 and x2 plus are basic variables, and others are non-basic variables. Let's set non-basic variables to 0 and solve for basic variables. x1 is equal to 3, x2 plus is equal to 3, and z is equal to 15. Now we don't have negative coefficients in row 0, so this tableau is optimal. The optimal solution is x1 is equal to 3, x2 is x2 plus minus x2 minus is equal to 3 minus 0 is equal to 3. s1 is equal to s2 is equal to 0. Z star is equal to 15. Also, the solution is the same as the one we got using the graphic method. Unrestricted-in-Sign variables are useful in modeling the changes among different periods. Let's see an example called production smoothing scheduling. A company is scheduling their production for the next 3 months. They already know the fixed demand for month 1 through month 3. There are 200, 150, 400 respectively. 4 types of costs are involved for each product. The manufacturing cost is $2,000 per product. If they're manufacturing more products than the demand for that month, there will be a holding cost at the end of each month, which is $500 per product. They want the production to go as smoothly as possible. However, because the demand changes from month to month, and there is a holding cost, they may need to increase or decrease production between 1 month and another. If they increase production, they need to hire more people and train them to operate the machines. There will be an extra $4,000 involved for each unit of increased production. If they decrease production, they need to release some people and it may hurt the morale. There will be an extra $3,000 involved for each unit of decreased production. 300 products were manufactured and they were all sold before month 1 started, so there was no inventory at the beginning. The company wants to minimize the total cost during the 3 months. For this type of problems, it is very important to define the appropriate decision variables. We let PT be the number of products manufactured during month T. T is equal to 1, 2, and 3. Let IT be the inventory at the end of month T. Let XT plus be the production increase from month T minus 1 to month T. Let XT minus be the production decrease from month T minus 1 to month T. So XT plus and XT minus cannot both be positive. The total cost is equal to the manufacturing cost plus the holding cost plus the increasing production cost plus the decreasing production cost. For the constraints, we have these 2 sets of relations. First, month T's inventory is equal to month T minus 1's inventory plus month T's production minus month T's demand. We can create these 3 constraints using this relation. Second, the production difference is equal to month T's production minus month T minus 1's production, which is also equal to the production increase minus production decrease. We can create these 3 constraints using this relation. This is a minimization problem. We can take the opposite of the objective function and maximize minus z. We only have the equality constraints, so we need to use the big M method to solve the problem. The optimal solution is this one. It means we always manufacture 250 products each month. We hold 50 at the end of month 1. And hold 150 at the end of month 2. We are not increasing production between different months. We decrease production by 50 from month 0 to month 1. The total cost is $1.75 million. Okay, that's how to deal with unrestricted-in-sign variables in the Simplex method and their application in the smoothing scheduling problem. Thanks for watching.